Hi there. Thank you for joining today's webinar organized by the American Cheese Society. And many thanks to our presenting sponsor, Dairy Connection Incorporated. A little bit about me, I'm Pat Polowsky, and today I'll be presenting What's the Crunch? The Crystals in Cheese. I run a website called cheesescience.org, and today's session is all about things that are often mistaken for mold, the crystals that are commonly found in many different cheeses. We're going to learn about how they're formed, some of the chemistry behind them, and hopefully by the end of it we have a deeper appreciation for something that a lot of cheese geeks love and enjoy. If you need to get a hold of me, you can find my info there at info@cheesescience.org. If you need to get a hold of the American Cheese Society, similarly related email, info@cheesesociety.org. And to check out more webinars, be sure to go to cheesesociety.org/ACS virtual programming, separated by hyphens, as you can see here. So without further ado, I want to dive in and talk more about cheese crystals, some of their underlying chemistry, and all the various types you can find across the wide variety of cheeses. And again, thank you to Dairy Connection for sponsoring this webinar and others for the American Cheese Society as well. So what exactly is a crystal? A crystal happens to just be an object that has a repeating structure, an orderly pattern. And we take advantage of that orderly pattern to measure them, to identify them, and to see them through various microscopic means, as you can see here. When you look at something like this, it may not look like it has an orderly pattern, but when you look at something like this over here, a different type of crystal, you can see some layers and some striations and some interesting geometry going on. And we take advantage of that when we go to detect these crystals. First, let's talk about different crystalline forms, or lack thereof. We have what are called amorphous things. Amorphous things are things that aren't crystals. They show no order, microscopically speaking. In our case, you can think of cheese as being amorphous. It's just sort of a hodgepodge of fat and protein, minerals, all sorts of interesting things sort of jam-packed together. There is some order in the idea that there's a structure of cheese, but there's no repeating patterns like you'd find in crystals. Then we have what are called polycrystals. These show regional order. These are little chunks of things that are regularly repeating patterns interrupted by things that aren't. The most popular example are the cheeses that you'd find on cheddar, calcium lactate, or cheeses you'd find in things like Parmesan, tyrosine, or leucine crystals. And then finally, we have single crystals. These are just individual crystals that show what we call global order. They themselves are one entire entity. You can think about a grain of salt being a single crystal as well. This happens to be a crystal from a piece of wash rind cheese, a crystal called ikite, which is calcium carbonate. But we'll get to more of that later. Just to get a deeper idea of what these actually are, you can think of this being the structure of an amorphous compound. There's really no order. These little orange dots here just represent the molecules or the atoms within that structure, and there's no really overarching pattern to its structure. Here you can see an example of a polycrystalline structure that shows regional order. There are some parts that happen to be orderly and others that aren't, interrupted in the middle here. So there's chunks of crystals interrupted by chunks of non-crystals. Think of the calcium lactate on cheddar as an example of that. And here you can see this is a single crystal. This is what we'd call global order. These repeating patterns are throughout the entire structure, as you can see here, this hexagonal packing structure. It may be hard to see the hexagon, but I can draw one here for you, that this is sort of the repeating unit that's being stamped over and over and over again. And this is what's giving that global order that we mentioned. And anything that you see that is basically a single grain of a crystal, like a grain of salt, for example, would have a global order like this. For our purposes, it's not too important because whether it's a polycrystal or single crystal, they're still crystals in cheese. They still usually have a crunch. But for scientists who try to analyze these, they can be important. And if you're trying to understand the chemistry, they can also be important because certain minerals may be more prone to one or the other, which would give you some insights into the cheese's chemistry and maybe why those crystals are there to begin with. Now let's talk briefly about crystal aggregates. Crystal aggregates are caused by crystals growing and merging into each other. So there are two steps of crystal growth. There's what's called nucleation, which is sort of the start of crystal growth, and then there's the actual crystal growth itself. So here we're trying to demonstrate nucleation sites, these little black dots, and as crystals are growing out, they grow further, and now we have the second stage, growth. So remember, we had step 1 here, nucleation. Step 2 is growth. But now they're going to merge into each other and form what we call a crystal aggregate. As you can see, these dots that were originally here have now merged into it. And at a macro view, not zoomed in, you probably wouldn't be able to tell that these started off as individual points, but now it's sort of just a light haze covering everything. And you can sort of see this midway on a piece of cheddar here. These crystals are aggregating together, forming a giant crystal aggregate. And if you ever see sort of the white haze on a cheddar cheese, that's what that really is. There's little tiny individual calcium lactate crystals that are aggregating together to form a crystal aggregate of calcium lactate that just appears as a sort of hazy or uniform sheet when it actually was distinct crystals at the onset. Now here's an example of crystals growing in real time. These are some crystals I put under a microscope, a supersaturated solution of alum, which is used in pickle making for anyone who happens to be doing pickling at home. It makes pickles have a crunchy texture. But here you can see these crystals growing in real time. Pay attention to these crystals sort of merging into each other. And as you can see here, these crystals are growing outwards. And you're getting some really interesting dynamics as these crystals are growing. Very cool stuff indeed. And now that we've learned a little more about crystal chemistry and what they're made of, hopefully we can get more into cheese making here soon. And here's that alum I mentioned. If you want to recreate this experiment at home, you can go pick that up at your local grocery store and you can try this for yourself. You can get a little microscope maybe off of Amazon, and you can sort of see this happening in real time. Even if you don't have a microscope, you can still make a supersaturated solution of it by putting it in some hot water. And as the water cools, it'll start to get hazy, and eventually you'll see a bunch of little chunks in there, which is basically like those sugar crystals used to grow when you were younger, except this is happening in real time, much quicker, but not nearly as tasting. So I think that might be the trade-off there. Okay, now that we've covered some of the crystal chemistry basics, let's dive into the crystal types in cheese and get specific with the kinds you can find in the cheese kingdom, so to speak. So when I think about cheese crystals and how we partition or think about them, I like to think of it in terms of a family tree. At the top of this family tree, we have mineral-based crystals and we have amino acid-based crystals, and from there we can get more specific. On the mineral side, we have things like calcium and magnesium. On the amino acid side, we have things like tyrosine and leucine. And I put a question mark here because it is possible there are other ones out there. We just haven't conclusively identified them yet. In fact, there can be a question mark after each of these because there probably are other types of crystals out there, but they're in small enough amounts or not enough people have bothered looking for them that we haven't accurately identified them yet. So still much to be learned. Very exciting. On the calcium side, we have calcium lactate as one possible crystal. And of course, it gets more complex from there. This wouldn't be a webinar if it didn't have some complexity. We have different forms of calcium lactate. We have what's called the L form and the DL form, and that just has to do with geometry. And one can be more influenced by microbial growth than the other. If one is less soluble than the other, you'll get it more often, the DL form. Then we have calcium phosphate crystals. One we've identified conclusively is brushite, which can be found things in like brie or bloomy rind cheeses. And again, I have a little question mark there because there could be different forms of that calcium phosphate that haven't been conclusively identified as of yet. And then we have calcium carbonate, and there we have some variety we can need to discuss. We have calcite and ikite, which is different hydrations or different forms of carbonate, calcium carbonate specifically, that are mostly found on wash rind cheeses, soft wash rind cheeses. For magnesium, we have magnesium ammonium phosphate, which is also found on wash rind cheeses as well. So now let's look at calcium specifically and talk about the minerals that you can get from calcium-based things. And as we know, calcium is very plentiful in milk and cheese, but I like to say that it's the glue that holds cheese together. If you zoom in on the structure of cheese here, what I'm trying to show, you can see these casein micelles being stitched together by calcium. Specifically, we call that colloidal calcium phosphate, CCP. It's actually pretty funny that in the dairy industry there already was a CCP before American Cheese Society came along and made that certification, which I thought was a pretty funny coincidence. But anyway, the calcium is the glue holding it together, so there's plenty of that calcium around as well. There's also some magnesium in there as well. Calcium is a +2 charge, as does magnesium, so they can be found interchangeably in the micelle, just a lot lower amount in the case of magnesium. Okay, let's keep on moving. And let's talk about calcium lactate crystals. Lactate is just another word for lactic acid, and lactic acid is formed by the starter culture. They ferment the natural milk sugar lactose into lactic acid. This process is known as glycolysis for the biochemists listening. We just know it as fermentation or culturing or even souring of the milk. The idea is these bacteria, lactic acid bacteria, LAB, as you might imagine, take this lactose and ferment it into this acid, and that's what does the acidification for many different types of cheeses. You can also add lactic acid as well, and some cheesemakers do that, especially in the cases of fresh cheeses like maybe fresh mozzarella. Okay, back to our family tree, and let's keep on moving along. Now let's look at calcium phosphate. That is what I'd say is a similar story to calcium. As I mentioned earlier, calcium is the glue that's holding cheese together. Like I said, it's actually a little more complicated than that. It's colloidal calcium phosphate. It's calcium and phosphate holding it together. So as calcium gets removed from the structure, so does phosphate, and that phosphate can be used for crystal formation just like the calcium can. And here I'm just sort of highlighting that phosphate bridge that's holding this calcium and the other phosphates together, and that's very plentiful in casein, the main protein in cheese. Okay, next up we have calcium carbonate. Carbonate is just a fancy word for carbon dioxide that's been dissolved in solution. As you can see, it just takes on a different oxidation and charge state, but for our purposes, you can think of carbonate and carbon dioxide interchangeably. And where might carbonate come from or carbon dioxide come from? Well, in our cases, smear microbes, the things on top of wash-drying cheeses, may consume lactic acid, and one of the byproducts they produce is gas of carbon dioxide. And all that carbon dioxide that's floating around in the aging space can dissolve into the surface of the cheese, turn into carbonate, and then be used for crystal formation, as we'll learn about in a bit. Now we can talk about magnesium and the magnesium-based crystals we find. As I mentioned earlier, magnesium is naturally found in milk, just at a lot smaller amount than the calcium. It can also be found in salt, especially things like sea salt, and then water. Hard water often contains lots of magnesium as well, so the amount of magnesium you find in cheese can actually vary depending on lots of things. What kind of water the milk was, what kind of water the cow was drinking rather, what kind of water the equipment was cleaned with, what kind of salt, and then just natural variations in the cow as well and how much magnesium they're putting into their casein compared to calcium. Okay, let's keep on moving and talk a little bit about minerals in milk and where they come from, because people often ask, are there other minerals in milk? Why don't we find those crystals as well? And here's a little graph showing the y-axis here is the amount of minerals, the x-axis here the different minerals we have. As you can see here, the main mineral you find in milk is actually potassium. And over here in this table, I've just sort of highlighted the numbers. The actual numbers aren't important. What we care about is a relationship. But we don't find potassium crystals in cheese, at least not yet. The only crystals we really find are calcium, phosphorus or phosphate, and magnesium. Why might that be? Why are the potassium and sodium not being used for crystal formation? Because the total mineral content is only part of the picture. That's the total mineral content in milk, as though you're drinking a glass of milk. When we need to talk about minerals in cheese, we need to look at the insoluble mineral content. That's the stuff that's sort of locked into the casein micelle, and that's what's going to be carried over to the final cheese. So here we can start to see some interesting relationships. Aha, calcium, phosphorus or phosphate, and magnesium are what's left. And sure enough, those are the crystals we find. And here I'm just sort of highlighting that relationship, the idea that some calcium, phosphorus, magnesium is carried through as insoluble minerals, leaving a nice little pool of potential crystal building pieces. Okay, let's get back to the fun and talk about the last few remaining types of crystals. Well, we talked about magnesium, but the specific magnesium crystal of concern for us is magnesium ammonium phosphate. Again, ammonium is just a fancy word for ammonia. Ammonia is NH3. In solution, it turns into ammonium, which is NH4+. But you can just refer that as ammonia. Anyone who's spent any time in any cheese aging spaces knows that they can reek of ammonia. And what's causing that is protein breakdown. Actually, any food aging space for that matter. If you ever cured meat, it also can smell like ammonia. As these microbes break down the protein in the cheese, they release ammonia because nitrogen, ammonia itself, is a byproduct of protein breakdown because those nitrogen groups are just a natural part of the structure of the protein you'd find in cheese. So anywhere there's surface aging going on, you're going to find lots of ammonia. And like before, that ammonia that was floating up here is going to dissolve partially into the surface moisture of the cheese and then be used for crystal formation potentially. Okay, let's see what's next. Here we have the amino acid crystals now, tyrosine and leucine. Amino acids are just the building blocks of proteins. So to go through the process a little bit, remember we have the structure and body of cheese, which is casein protein. And that is really what's the backbone of cheese itself. That got carried over from the milk, which is about 80% casein. Most cheeses are about 100% casein because the whey got drained away with the whey. But as that casein protein ages out in the cheese, with time, it can break down to what are called peptides. These are protein pieces, so to speak. That can happen just through the action of age, through intrinsic enzymes within the milk or within the cheese, through the action of microbes, or some of the rennet could be doing this since rennet breaks down protein, or maybe the cheesemaker added flavor-producing enzymes that encourage protein breakdown. All that can be happening. And of course, the process really gets complete when you get the final little building block of these peptides, which are individual amino acids. So if you think about it in reverse, amino acids get chained together to form peptides. Those peptides get chained together and form bigger complexes, just known as regular old proteins. And caseins is a really, really complex arrangement of peptides and has lots and lots of thousands and thousands of amino acids. But as these break down, these amino acids sort of form in solution. You can think about if you get something that's super saturated in solution, it can crystallize out. And that's what's happening with these amino acids. So just like we did before, there's lots of amino acids, and there's lots of amino acids in milk and cheese. I mean, anyone who's done any biochemistry knows, there's 20 amino acids and such, 9 of them, 10 of them being, who knows, essential, those kinds of interesting nutrition facts. But why have we only found 2 so far, tyrosine and leucine? Well, the answer comes down to one key word, solubility. So to help understand that, let's look at this little example. So here we have 3 amino acids, again, the building blocks of proteins, in Parmesan cheese. I took these data just from a few different data sources you can see down here. These data weren't about crystals at all, but this serves as a good example. Now this little graph we have here, these blue bars on the y-axis are basically how much of that amino acid there is. The x-axis here are the different types of amino acids, just abbreviated. Tyrosine and leucine, phenylalanine, alanine, glycine, serine, lysine, glutamate, like that's the building block of MSG, aspartate, those kinds of things. Everything's very abbreviated here, but you don't need to know too much or be concerned with that exactly. What this red bar shows is the solubility. So basically what that means is if the amount of amino acid gets above this bar, it'll form a crystal. And I'll try to draw my crystal right here all the best. If it's below this bar, you don't get a crystal. No crystal. Yikes, my handwriting's pretty bad, but you don't get a crystal if it's below that bar. So now we can start to see what might be going on. Quickly glancing at this, you can see only 2 amino acids have reached the necessary amounts to be over the solubility threshold. We have tyrosine and we have leucine. As you can see, there's not much tyrosine in cheese at all. In fact, there's very little, but its solubility is so low that the second you get enough free tyrosine formed, aha, you're going to get crystals. And here we go, I'll draw a star for that. Leucine's a similar story. There's lots of leucine, and it's able to go over its solubility threshold very easily by a huge amount, and you get lots of crystals of that as well. And even though there's high amounts of other types of amino acids, like glutamate, everyone knows Parmesan cheese is supposed to have that umami flavor because of the glutamate. It has such a high solubility threshold and never reaches the point where you'd get the formation of crystals. So that can help sort of explain why you only get certain types of amino acid crystals in cheese, at least the ones we've discovered so far. Things might be different because sometimes microbes can help form crystals, as we'll learn in a little bit, and that might change some things around. But so far, tyrosine and leucine, these two are the only ones we've discovered, and the reason they're so prevalent is that they form in such high amounts they cross their solubility threshold, which is sort of basic chemistry. Just want to really hammer home that point, that's why that's going on there. It's not that there's something special or unique about those as far as they're magical or something like that. Cheese crystals are indeed magical, but as a whole, not as an individual chemistry level. So there you go. This is the main family tree of cheese crystals. There's a wide variety, all different types and sorts. Lots of interesting things to learn here. Perhaps one of the most interesting things, though, is that 5 to 10 years ago, this is what that tree looked like. 5 years ago, 10 years ago now, I guess I can tell you that I've been working on this for a while, so I forget what time it is, but we've had about half as many cheese crystals that were discovered as there are now, which is really interesting to think. The work done by Paul Kinstead at University of Vermont and people like Dr. Gil Tansman, they all did a lot of work to discover these types of crystals, and they've definitely filled in this family tree quite a bit and left us with a lot to learn. But I'm hoping one day that this family tree will even be broader and even have more crystals to show us as well. Very much looking forward to that day as well. If you'd like a one-stop shop and sort of a simplified form of that family tree, or if you want to see an interactive version of that family tree, you can check out this website here, go.uvm.edu/crystals. And that is a summary of all the work I did while I was at the University of Vermont with Dr. Paul Kinstead, and I was following the footsteps of some cheese crystal giants like Dr. Gil Tansman or Dr. Pallavi Rajmandari, who were both really good friends of mine in the dairy world. And they did a lot of the preparatory work necessary for some of this outreach work I was able to do. And one of such things is this infographic that you can download, hang up, keep it next to your bedside if you need to wake up in the middle of the night from a nightmare. This will put your mind at ease looking at these beautiful pictures of cheese crystals. So please do check it out if you do get a chance. And there's lots of other interesting things on that website as well, including a history of cheese crystals going back over 120 years. Lots of cool things related to cheese crystals. Okay, now since we've learned a little more about the chemistry and where all these pieces of the crystals are coming from, now let's apply it and contextualize it and figure out which cheese types you can find these crystals and maybe some interesting pictures of how they present. So I like to break down crystals by cheese type into 4 main groupings, and the next few slides are going to take us to those 4 main groupings. I wouldn't be a real academic if I didn't hand wave and waffle a little bit and say it's a little more complicated than this. There could be other groupings. There could be cheese crystals that appear in another cheese, not another cheese by some strange reason. But in general, if you follow this guidance, that'll get you 99% of the way there as far as knowing what type of crystal you're dealing with. First, let's talk about cheddar style cheeses. And this is usually more for aged cheeses, aged cheddars. It's possible to find crystals in younger cheddar style cheeses, but usually something went very wrong with the make process. Either there was a rogue microbe there causing some wacky things to go on, or way too much acid was formed, or the cheese was temperature abused, which caused pronounced crystal formation. But such crystals would be lactic acid crystals combined with calcium, known as calcium lactate. So this is an example of what lactic acid is. Again, remember, this came from the lactose. The lactose broke down by the starter culture bacteria, the lactic acid bacteria, LAB, and it formed lactic acid. This is just an example of what makes an acid an acid. This guy over here is what's known as a proton. And that's just what we measure when we talk about pH, the H in pH. Well, here you see where that H comes from, but that's beside the point. What we care about is this lactic acid molecule over here. If you get 2 of those combined with this calcium, you get calcium lactate crystals. And why 2? Well, it has to do with charge balancing effects. Calcium has a +2 charge, as you can see here, 2 plus, and you need 2 minuses to cancel it out. So you need 2 molecules of lactic acid, 1 atom of calcium, and 1 ion of calcium, I should say, for the pedant chemists listening. And with that, you get lactic acid crystals, specifically calcium lactate crystals. Oftentimes, how you'd find these is on the surface of a cheese. So here you can see an example. This is a really aged block of Wisconsin cheddar. I believe this was a 15-year block of Wisconsin cheddar. As you can see, it's absolutely coated with calcium lactate crystals. Those aren't mold. A lot of consumers mistake this for mold. In fact, this is probably the most notorious crystal type across all cheeses because it's so often mistaken for mold. And a lot of education needs to be done teaching people to know it's a natural part of the cheese aging process, and many would find it as a marker of a well-aged piece of cheese. If it has crystals on it, it usually means a little older, it has better developed flavor. Not to mention an interesting textural element that adds a little bit of crunch. People usually like some contrast, right? Sweet and spicy, sweet and sour, soft cheese, crunchy crystals. I think they go together really well. Another place commonly found is sort of any divots in the cheese, any place that moisture can pool. In this little divot here, or maybe there's a buckle in the packaging, a loose packaging around it, water can pool, or free whey, any residual whey can pool in there, and that's going to dissolve some of that acid. It's going to go into there. Some of that calcium, here I'll draw calcium real quick, some of that calcium can flow into there, and they can mix together and crystallize out. And that's why you often see calcium lactate crystals in either the dents on a surface of a cheese or where the packaging was loose or there was a little fold in the packaging, all because moisture can gather there, and moisture makes the perfect little bath for calcium lactate crystals to form. Now let's talk about surface ripened cheeses. Specifically, I'm going to talk about soft surface ripened cheeses, sometimes called smear ripened cheeses, but this can also apply to hard surface ripened cheeses as well, things like Gruyere, for example, or Appenzeller, those kinds of things. But for the soft ones, think of cheeses like Limburger, or really smelly cheeses like Revolution Style that you'd find in from Europe as well. And we find two main types of crystals in surface ripened cheeses. We find a crystal called Eichite and a crystal called Struvite. There's also another one I didn't mention here, which is Calcite, which is just a different form of Eichite. But Eichite's the one we find very often. It seems to be, at least for the ages in which we get the cheese, it seems to be the common one. You get them really young, maybe you find more calcite, or maybe very old, you find more calcite rather. But Eichite, as you can see here, is a calcium carbonate hexahydrate crystal. That just sounds really complicated, just a way of saying calcium and carbon dioxide combined together, as you can see there. Here's the calcium, here's the carbonate. This 6H2O just means it needs some water to form this crystal type. And then we have struvite, which is magnesium ammonium phosphate hexahydrates. Again, just a complicated way of saying you have some magnesium, some ammonium or ammonia, and some phosphate or phosphorus. And remember, we can trace back each one of these pieces to where they came from because we learned earlier about some of the chemistry. But first, I just want to take a second and appreciate some of the visuals we see here. These are falsely colored images. This is under what's called polarized light, which sort of alters how you see crystals. It makes them show up really bright against amorphous materials. For example, like this is a piece of cheese here. That's why it's not really shiny and strikingly bright versus all these other things are the crystals. These crystals themselves are basically perfectly transparent or maybe a little hazy. They don't look orange or don't have different colorings like this. They don't look like rainbows, unfortunately. That just has to do with the filters used for this image, something called birefringence. For any physicists or light optics people listening, that's what's going on there. But back to our original point and say let's trace back these molecular pieces, the calcium, the magnesium, and such, and where did they come from? Sure enough, it has to do with everything we covered earlier when we talked about the cheese crystal chemistry. Calcium and phosphates and magnesium, remember, all come from milk and result in the cheese itself. Remember, calcium and magnesium are the glue that hold that casein micelle together, as is phosphate. So all this is in the casein, which is the main structural component of cheese. So there's lots of it available for crystal formation. Then we have microbial ripening, and that's both primary and secondary to crystal formation of these cheeses. The primary way you can think about it is the surface microbes, the smear bacteria, consume lactic acid and produce carbon dioxide, and they consume protein and break it down and produce ammonia. These dissolve into the water and you get carbonates and ammonium, and those combine with the aforementioned minerals and you get those crystals, calcium carbonate, magnesium, ammonium phosphate. But these microbes also have a secondary effect, and they can do what's called biomineralization. The microbes growing on the surface here can sort of preferentially suck up some of these minerals and take an active role in forming these crystals. You can think of it sort of as like it's just a byproduct of what they're doing. They're sort of sucking up these minerals for food, they use them up, they die, and maybe they help form crystals from where they were beforehand. So both primary by producing the pieces needed for these crystals, and also secondary by taking an active role in forming these crystals through a process called biomineralization. And then finally, I like to call the X factor, or the external factor. Magnesium and perhaps even some other minerals, calcium for the example, or phosphate, can get into this cheese or milk through various means. And we already mentioned that earlier. Salt and the water are two main ways that magnesium can get into milk that wasn't there originally as part of the casein micelle. And maybe you have lots of magnesium, you could get more likely to get some of those crystals perhaps. Now let's talk about blue cheese. I give blue cheese its own section because it's an interesting hybrid of different types of crystals we just talked about. These are the three main types of crystals you most likely will find in blue cheese. You'll find tyrosine, leucine, and brushite. Tyrosine and leucine, these two guys here, remember, these are amino acid crystals. And if you remember, amino acids are what result from protein breakdown. All that mold growing in these eyes gets in there and it breaks down the protein, it forms amino acids, and they grow to a large amount and sort of crystallize out. Brushite, on the other hand, that's a mineral-based crystal. Remember, that's calcium phosphate. That's what the structure of brushite is right here, calcium and phosphate. And a similar thing is happening here where acidity is being changed because the blue mold's either consuming the acid or it's producing ammonia, which is sort of buffering or changing the acidity. Those minerals, their solubility changes and you get those minerals forming as well. And it really is like a hodgepodge soup of all these different types of crystals. You can see here in this little cavern here, there's different crystals. Here I took some blue cheese and actually just mashed it up and filtered it, and you see lots of little white speck crystals there as well. And here's an example of a smear ripened blue. So we just looked at soft surface ripened cheeses before, and here's a blue cheese where they decided to treat the rind in a similar way they would for a traditional surface ripened cheese. And sure enough, we get the same crystals. We get ikite, we get struvite. And the reason I'm showing you this is it's really how the cheese is made and the chemistry of the cheese that determines what kind of crystals you're going to get. It's not the actual type of cheese itself. For example, if you were to make a Comté, but instead of making Comté, you made it in the style of a cheddar for some reason, and you still called it a Comté, you would not get the same crystals you would get. You'd get the crystals more like a cheddar. And the reason I say this is sometimes it trips people up and, you know, oh, I thought cheddar always has to be calcium lactate. It's like, no, if they're making cheddar like they would a Parmesan cheese, which is very common nowadays, sort of what you'd call a sweet cheddar, maybe you will get some amino acid crystals like you would in the Parmesan cheese. And that's what's going to bring us to our next and final grouping of crystals here. The aged Italian, Dutch, and Alpine style cheeses. So for Italian, you can think of things like Parmesan cheese or Parmigiano Reggiano if you're talking about the traditional stuff. The Dutch cheese can be things like Gouda over here. I'm showing a picture of that. And then Alpine, that can be anything. Emmental, Gruyere, Comté, all sorts of interesting cheeses. And what's going down there, as we mentioned earlier, here's just looking at a different way, is protein breakdown. So we have that cheese protein, and remember, it's broken down into smaller pieces known as peptides. That's what I'm trying to show here. And these peptides here are made of individual amino acids. So as you might imagine, some enzymes or microbes might get in here and break these up even further. And then we get individual amino acids. Specifically, as we mentioned earlier, the two that surpass their solubility threshold are tyrosine and leucine. And here you can see a picture. This is some tyrosine in the eye of a piece of Comté or Gouda, I believe. And here's actually an interesting leucine crystal I found in a piece of mimolette while I was at the University of Vermont. And it was just pure leucine, and very interesting crystal. And in mimolette, who'd have thunk it? But these crystals themselves are quite beautiful if you zoom in on them, and that's what I was trying to show here, that here's the eye of a piece of Gruyere, I believe, and if you zoom in on that, this is sort of what that tyrosine crystal looks like. And if you zoom in even further, you start to see some really nice, interesting structure here, and it almost looks like a snowflake. And I do like to refer to crystals as sort of the snowflakes of the cheese world. No two are the same, and they're quite beautiful and striking as well. With that, I'd like to thank you for your attention and for listening to this webinar. And again, many thanks for Dairy Connection for sponsoring this session, and many thanks for the American Cheese Society for organizing such a great venue to talk about cheese and do some educational endeavors. Thank you.